Hi there, in this video we're going to continue our discussion of the rules of probability, moving on to the multiplication rule. So this is part 3 of our rules of probability video series. So we have, in order to get to the multiplication rule, first we need to figure out what does it mean to be independent. When you have two or more events, what does it mean to be independent? So two events are independent if the occurrence of one does not affect the probability of the occurrence of the other event. And then events that are not independent are called dependent. And so with dependent and independent events, oftentimes we want to know that given the one event has occurred, what does it mean for the probability of the other? So that's what this notation means. P of B/A, that tells you, that is the probability of B given that A has occurred. So that's what that means. So I'm looking over here. This represents the probability of event B occurring after it is assumed that event A has already occurred. And so it's red, the probability of B given A. If two events are independent, then the probability of B given A is just the probability of B, right? If they're independent, that means that the occurrence of A did not affect the occurrence of B. So the probability of B is just whatever the probability of B is without regard for A happening. So let's try some examples. Decide whether the events are independent or dependent. So in our first example, event A is selecting a king from a standard deck of 52 cards without replacement. And then event B is then selecting a queen from the same deck of cards. So what does without replacement mean? So that means you select a king from the standard deck of 52 cards and you don't put it back. So are these independent or dependent? We will say that these are dependent, right? Because after you take the king out, so the probability of getting a king is what? There are 4 kings out of 52 cards. So that's the probability of getting a king. But now, once you don't put that card back, how many cards are in the deck? Right? There's no longer going to be 52 cards. Now they're going to be 51 cards. So we can say after the king is selected, 51 cards remain. So that's why they are dependent. So that means that the probability of getting a queen would be, there are 4 queens, but now out of 51 cards. So the occurrence of selecting a king did affect the probability of selecting a queen, right? Because now we're not saying 4 out of 52 cards, it's 4 out of 51. Now what about example 2? Decide whether the events are independent or dependent. Driving over 95 miles per hour and then getting into a car accident. This is kind of subjective probability, right? Based on experience, based on our prior knowledge of speeding, we can say that yes, speeding, going over 95 miles per hour, increases someone's chance of getting into a car accident. So we will say that these are also dependent. And we're going to say this is subjective probability. Remember, subjective probability is when we make when we decide a probability based on experience, intuition, an educated guess, things like that. So this is subjective probability. So what does it mean to say without replacement? So let's talk about that for a minute. So without replacement, that we discussed up here is that once you take an item out of the sample space, you don't put it back. So not putting that item back, then it's going to affect the subsequent probabilities. So essentially without replacement means you're always going to have dependent events. So let's say this. So probability without replacement means once we draw an item, then we do not replace it back to the sample space before drawing the next item, right? So essentially an item cannot be drawn more than once. So last week we were doing something with the M&M bag, so picking a candy, and we were putting it back, right? So I was saying in the activity that you turned in that when you pick a candy out, note the color and then put it back in the bag. So that will be with replacement. So that means that that candy can be chosen again. Without replacement will mean that you take that M&M, you note the color, and then you leave it out of the bag, and then you pick another M&M, and so on. So that then is changing then the number of M&Ms that are left in the bag versus when you put it back in, you still have the same number and you have back the original sample space. Now that we understand a little more about independent and dependent events and replacement, let's talk about the multiplication rule. So the multiplication rule is when you have a probability that of A and B. So the probability that event A occurs in the first trial and event B occurs in the second trial. And so the probability of A and B is equal to the probability of A times the probability of B given that A has occurred. Remember, this means the probability that of B given that A already occurred. So this also tells us that the probability of B given A is the probability of A and B divided by the probability of A. Again, just do some quick algebra here. If I wanted to solve for this, divide both sides by P of A, the probability of A, and then you'll get this equation. So to find the probability that event A occurs in one trial and event B occurs in another trial, we multiply the probabilities. But be sure that the probability of event B is found by assuming that event A has already occurred. So this is a little bit different than when we had the probability of 4 and even, right? So that is that they occur at the same time versus this is you're doing multiple trials. And so you're doing event A first and then event B happens. So when events A and B are independent, the probability of A and B is the probability of A times the probability of B. And this essentially comes from what we talked about earlier here, that if events are independent, the probability of B given A is just the probability of B, because then the probability of A doesn't affect B. And so that's what that says. So let's try this example. 2 cards are selected in sequence from a standard deck of 52 cards. The first card is not replaced before the second card is chosen. Find the probability that both cards are aces and write your probabilities at reduced fraction. So what does it mean to say the first card is not replaced? I know it's kind of funky wording, but not replaced, so that means without replacement, so it was not put back in the deck of cards. So let's see, so the probability of A and B. So let A be the first card is an ace, and B, event B, is that the second card is also an ace. So we're trying to find the probability of A and B. So based on our formula, right, the probability of A and B will be the probability of A times the probability of B given that A happened. Are these independent? No, right, because this is without replacement, so these are dependent. So these are dependent events because we have without replacement. It was not replaced. So what is the probability that the first card is an ace? How many aces are there? There are 4 aces out of 52 cards. Now what about the probability of B given that A happened? So B is the second card is an ace. So what is the probability of getting an ace again, knowing we already got an ace? Well, now since we already got an ace and we didn't put it back, instead of 4 aces, we're going to have 3 aces left. And because we didn't put it back, instead of 52 cards in our sample space, now we only have 51. And so here you multiply those fractions. How do you multiply fractions? Numerator times numerator, denominator times denominator. So I'm going to have 12 divided by, when you put that on our calculator, I got 2652. And make sure that you reduce that. So it looks like I'm going to start by twos. Sometimes it's easier to start small. So if you reduce by twos, what do you get? I know 12 divided by 2 is 6, and then 2652 divided by 2, I get 1326. That's both of those are still even, so that means I can continue. So divide by 2 again. If you see right away something higher to divide by, then that's fine. So this will be 3 over 663. And I think maybe that's as far as you can go unless 663 can be divided by 3, which actually you can. So this will be 1 over 221 is what I got. And so that will be our reduced probability. But the main point here is that when you have dependent events, you have to figure out the probability of B happening given that we know the result of A. So here, that the second card is an ace, knowing that we had gotten an ace already. So notice how that changed. If we did it with replacement, so when you put the card back, it would have been 4 out of 52 and 4 out of 52, and the events would have been independent because our sample space goes back to being the same. Which brings us to Bayes' rule. So Bayes' rule essentially extends the discussion of conditional probability to include other applications. So it's revising a probability value based on additional information that is later obtained. So essentially the probability of A given B is the probability of A times the probability of B given that A occurred divided by the probability of B. So what this tells us is how often A happens given that B happens, and when we know all this other information, right? So when we know how often B happens given that A happens, and how likely A on its own is to happen, and how likely B on its own is to happen. And so then we can kind of figure out this new probability. So this example, swimming in the lake, right? You're planning to swim in the lake today, but the morning is cloudy. And so you're like, oh no, 50% of all rainy days start off cloudy. So then what are your chances that it's going to rain? And then you go to other information, but cloudy mornings are common. About 40% of days start off cloudy. And this is usually a dry month, and so only 3 of 30 days tend to be rainy, or 10%. And when I was thinking about this, I was thinking about August, so thinking about a dry month. What is the chance of rain during the day? So that's what we want to know. What is the chance of rain? So we will use R to mean the rain during the day and C to mean cloudy morning. So what we want to find is the chance of rain given that it's cloudy. And so we have all this information, right? 50% of all rainy days start off cloudy, but cloudy mornings are common, 40%. And so how do we put it together into our formula? So taking this probability of A given B, so for our purposes, it's going to be probability of rain given that it was cloudy. So the probability of rain given that it's cloudy is going to be our probability of rain on its own times the probability that it's cloudy given that it rains, right? This is a probability that we will know. So that's, which one is that? This one, 50% of all rainy days start off cloudy. And then the probability of just being cloudy. So putting it together here, we have the probability of rain is 10%. The probability of that it's cloudy, given that it's raining, is 50%. And the probability that it's just cloudy in general, most days are cloudy, is 40%. So putting it together, we get this. So this is using Bayes' rule. And so we end up with just 0.1 times 0.5 divided by 0.4. All these different probabilities, which only gives us a 12.5% chance of rain. So it's not too bad. So you can definitely go then for a swim. And so it just gets a little convoluted, right? There's a lot of data in here. Going back to the idea of one of the examples I did in a prior video, a table is really helpful in organizing our data. So I'm kind of set up a table here. We'll move it up so we can use it with our data that we have. So I know that we're looking at rain versus cloud. So it's either cloudy or not cloudy. So then I put those in there, and then I'm looking for the probability of rain given cloud. So I know that those have to intersect somehow. So that's why there, rain, I put it in rows, and clouds, I put it in columns, but you could have reversed that. And so let's look at what we have, right? So I know that the probability of rain on its own is 10%. So that is the entire probability of rain. So this is rain, so the probability of rain is 10%. So let's say 0.1. I guess we could leave it as decimals, or I mean as percentages. So 10%. So that means, well, let's look at what else do I have. And let's go to the entire probability of being cloudy. The probability of being cloudy is 40%. So cloudy is over here. So this is going to be 40%. So those are my probabilities. Now, one thing that we know about probability is that probabilities are always between 0 and 1. So in percentages, the probability of something occurring is between 100% and 0%. 0% meaning it never happens. 100%, it always happens. So that means that these should add up to 100, right? If I'm looking at percentages. So the total should be 100. So this kind of helps me then figure out, well, if my total should be 100 here, 40 plus what gives me 100? So that will be 60. And then 10 plus what gives me 100? So that will be 90. And so now what's going on in here? So let's go back to now my given probabilities. So the probability of cloud given rain is 50%. So half. So the probability of cloud given rain. Now here I have to be careful, right? Because it says 50%, but I really want to think of that as half. And so, because notice that if I put 50 here, I'm going to have a problem because 50 plus what equals 40. So that's not right. So instead, that's why I kind of want to think of it as half, because the probability of cloud given rain is half, right? 50% of the total. So that means it's going to be really 5% here. I know it says 50 there, but it's really 50% of those days, right? So here, let me say 50% of rainy days are cloudy. That's what that says. So if my percent of cloudy days, of rainy days is 10%, then cloudy is half of those. So 5% of those will be rainy days or cloudy days. I hope that makes sense. And so now I think I have enough information to finish the chart, right? So let's finish the table. So what, 5 plus what gives me 40, right? 35. And then now that I have those, I can figure this out. 5 plus what gives me 10? 5. And then 35 plus what gives me 90? Or you can think 5 plus what gives me 60? And so that will be 55. Okay, so now we are looking for, so from the table, I'm looking for the probability of rain given cloud. And just to double check, right, notice that if I want from here the probability of cloud given rain, this will mean that I want the probability that is cloudy, so that's 5% out of the total rainy days. So 5 out of 10, which is 1/2, which is 0.5, which is 50%, right? So now here the probability of rain given cloud is going to be the probability of rain and cloudy. So that again will be 5, but now I'm dividing by the cloudy days. so it's 40. So 5 out of 40 is reduce that. So what's that? That's 1/8, right? Because 5 goes into 48 times. And then when you do that as a decimal, that's 0.125. Hey, that's the same thing we got using the formula. So this still gives you 12.5%. So I wanted to do that just to show you that using a table can also help you and be in, if you're a visual learner. I tend to be more visual than what's the other one, kinesthetic, like doing it, or visual, or what's the other one, listening. uh, Auditory. Thank you. Well, I'm sure you guys were saying it. I'm hearing you. So 12.5%. So I wanted to just do the table because sometimes looking at these formulas can be daunting or may seem confusing. And how do you get all that data and organize it? And how do you decipher things from it? So having a table can make things a little bit better, right? Like here, the probability, just to verify that the probability of cloud given rain is 50%, we can do that here. The probability of cloud is 5 out of rain, which is 10. So it would be 5 out of 10, which does give me 50%. And what I'm looking for is the probability of rain. So still that same 5, but now out of clouds. So out of being cloudy, which is 40%. So 5 out of 40, it still gives me the 12.5%. So the table can be a straightforward way of finding these conditional probabilities, but then the problem is, how do you set up the table? So getting good at setting up the table and having lots of practice will be really helpful in doing these types of problems. So let me do another example, the COVID problem. All right, so let's look at this example. During the development of the COVID-19 testing equipment, in a sample of 10,000 individuals, there were 1,000 infected individuals and 9,000 not infected. Of the infected persons, 950 will be detected by the test, so those are true positives, and 50 will be missed, so those are false negatives. And then for the uninfected, the 9,000 uninfected people, 8820 will correctly have negative tests, so true negatives, and 180 will be positive, so those are the false positives. And this is data that I got from the CDC. So when they were in development of the different COVID tests that we now use. So denote in the event of having COVID-19 by C, find the following probabilities. So the probability of having COVID-19, and then find the probability of having COVID given that a positive test result was had. So how do we do this? And so notice again, right, that this is how you're going to get a probability problem, and it's a little overwhelming. And so how do you get all the different pieces? You can kind of start by writing your own notations, right? There are 10,000 total. There are 1,000 infected individuals, so they had COVID, and 9,000 not infected. And then there are all these other numbers. So this is where I believe, and I hope that you agree, that a table comes in handy in terms of organizing your data. If you don't need the table, then you don't need to have it. So I organized it so here. And how do you know how to organize it? I know, well, there are people who have COVID and don't have COVID, and there are people who are testing positive and testing negative. So that's how I then organize it. My positive test result, negative test result, and then has COVID or no COVID. So like the true positives, for example, that means they have COVID and they have a positive test result. So that's how I know like what should be in a column and a row, like if they are supposed to intersect, right? So that means that, so I shouldn't have positive test result and has COVID both in columns, because then they're not going to meet. A true positive means the person has COVID and they have a positive test result, so I want them to intersect, right? To meet at a T. Or I don't know. Okay, so I know there were a total of 10,000 individuals and 1,000 were infected. So I know then my total is 10,000, so total of people is 10,000, and 1,000 had COVID. 9,000 did not, right? So then let's make sure those do add up to 10,000. That's good. And now let's go back to the rest of the information. Of the infected persons, so the ones that do have COVID, of the 1,000, 950 will be detected by the test, so true positives. So 950, so they have COVID and they tested positive. So 950 have COVID and tested positive. So these are my true positives. So in order to add up to 1,000, that better be 50. And I believe this number was given to us, and 50 will be missed. Yes, so that number was given, but oftentimes you may not be given that number. However, given if that's missing, we can just figure it out. And then for the 9,000 unaffected people, 8820 will correctly have negative tests. So meaning they do not have COVID and they tested negative. So what was it, 8820? So that means they don't have COVID and they tested negative. So 8820 will be over here. And so to get to 9,000, what's the other one? You can subtract, or you can look at here. 180 will be positive. So the false, 180, and now we can find our totals for the bottom here. So 950 plus 180 gives us 1130, and then 50 plus 8820 gives us 8870. And now make sure that those together add up to 10,000, which they do. So this should add up to 10,000, and those should add up to 10,000. And so now, what am I looking for? I'm looking for the probability, well, first the probability of having COVID. So the probability of having COVID will be has COVID, so it's 1,000 out of 10,000, which will be 0.1 or 10%. Now, the second probability is the probability of having COVID given that a positive test result occurred. So having COVID given that a positive test result occurred. And this is where Bayes' theorem will come in and say, okay, you will have to do this formula, right? So then it will be the probability of having COVID times the probability of having a positive result given that you had COVID divided by the probability of positive result. So we can do it that way, right? So I know the probability of having COVID is 0.1, 10%, times the probability of having a positive result given COVID. So the probability of positive result given COVID is 95%, right? 950 divided by 1,000. So it will be 0.95 divided by the probability of getting a positive result, which is positive results 1130 out of 10,000. And this will give us our probability. So we should get 0.84 something. So that's using Bayes' theorem. But organizing it with the table, I can just say, well, the probability of having COVID, given that it was a positive result, will be 950, right? Has COVID and positive result out of 1130. So from the table, I can just grab that information. So it'll be 950 out of 1130. And so when you do that on your calculator, what do we get? We also get 0.84. And so you can use Bayes' theorem and do the formula, or if you are able to organize your results into your data into a table, it is visually a lot easier to get, right? So the probability of COVID, given that it's a positive result, will be COVID and positive result 950 out of a total of all the positive results, 1130. When I want the probability of positive result given COVID, then it's 950, but now out of 1,000 because the given is that the person has COVID-19. So my denominator changes based on whatever my given is. Okay, so I hope that this helps with all these concepts. Start your homework as soon as possible so that you can practice the concepts and be ready for the quiz next week. Contact me if you have any questions.